Today we are going to discuss gamma and exponential distributions. So already we completed normal distributions in first part of unit 3. Okay, so there we learned that one. So what is what importance of normal distributions, applications of normal distribution, and how to draw probability density curves, and by using normal curves, how to write that values. Okay, so those things we saw that, and one more thing we saw that in normal distribution that is symmetrical about mean, and mean is equal, mode is equal to median, which is equal to mu, and mean deviation about mean is 4 by 5 times of standard deviation approximately. So all those things we saw that, and we saw the problems on normal distributions. So here it is, we are going to discuss gamma and exponential distributions. So these two distributions are also coming under continuous distributions. Okay. So what is the meant by continuous distributions? It takes all the values in the interval continuously. So it means we give the range from minus infinity to plus infinity. In that, we have to check each and every value. We need to check that one. Okay. So here it is. We are going to discuss two distributions. One is gamma distribution. Another one is exponential distributions. Okay. So of course, so normal is by using normal distributions, we can calculate the problems by using the density functions. But some of the density functions, it may not possible to calculate by using normal distributions. So for that, we are by using gamma distributions, we can easily calculate such type of density functions. And exponential distribution is a special case of gamma distribution. So there we said in normal distributions we have two parameters, right? So mu and sigma. In the same way here gamma distributions we have two parameters, alpha and beta. And by taking alpha is equal to 1, then we get exponential distributions. So for that, just we are giving introduction here. So the normal distribution can be used to solve many problems in engineering and science. Of course, numerous situations that require different types of density functions, and those distributions here we are saying gamma and exponential distributions. So mainly where we use these distributions, here it is in queuing theory and realistic problems. So here it is we use mainly queuing theory and reliability problems, we use that one. So in that case, we say that time between arrivals of service facilities. It means that in queuing theory, we discuss about so service providing as well as time arrival. So it means that if you are taking railway station, there it is having counters. So for providing tickets or for giving inquiries, okay, for giving help desk. Okay. So there it is. We are going there and we form a queue for taking service, right? So that is how much time is taking for providing service for each passenger. Okay. So that is we can use by using gamma distributions. We can say that easily that. And in the same way, reliability problems is difficult problems also we can calculate by using gamma distributions. Okay. And next, exponential distribution is the special case. Already we said that one. And here also one of the thing we are saying where we apply this one applications of gamma distributions, electrical systems, and often are nicely modeled by the exponential distributions. And before going to gamma distribution, first we see the basic things of which is coming from gamma function. So this is very well known in people in first beta people learn that one beta and gamma functions. And gamma functions here we are seeing first what the definition of gamma function is defined by gamma n is equal to e power minus x x power n minus 1 dx per n greater than 0. Gamma function is converges for n greater than 0. And next another properties we are using, one is gamma 1 is equal to 1. Of course already we proved all proofs already we learned in your first BTech level. So gamma n plus 1 is equal to n into gamma n, or some of the cases we can write same formula. Gamma n is equal to n minus 1 into gamma n minus 1. So this is also we use n minus 1 into gamma n minus 1. And next one more thing, gamma n plus 1 is equal to n factorial. Okay. So gamma n plus 1 is equal n factorial. And gamma function is defined only for positive 1. Okay, so this is not applicable for negative 1. So these are the important one for entering into gamma distribution. So gamma n is equal e power minus x power n minus 1 dx, and gamma 1 is equal to 1. Gamma n plus 1 is equal to n into gamma n, and gamma n plus 1 is equal n factorial. Now we are going to see the definitions of gamma distributions and exponential distributions after that. So we'll see that statistical measurements or statistical parameters of gamma distributions and the exponential distributions will calculate. Nothing but mean, variance, standard deviations. We'll see the proof of those things. Okay. Here it is. First, we see the definition of gamma distribution. The continuous random variable capital X has a gamma distribution. So simply you need to remember that. So normal distribution is continuous random variable X has a normal distribution with the parameters mu and sigma. So just if you learn one definition, based on that you can write the rest of the definitions. Okay. Why? Because it starts with the same as this, the continuous random variable. Normal distribution, gamma distribution, and exponential distribution. And normal means normal will write and parameters will write. And its density function is given by. So this is the density function we are using f of x alpha beta. This is nothing but simply we say that parameters of gamma distributions. Same this one we can write this one also like as f of x is equal. So f of x is equal. So 1 by beta power alpha gamma alpha x power alpha minus 1 e power minus x by beta where x greater than 0. So here is having exponential function. This is an increasing function. And one more thing here we are using simply to see that gamma definition, right? See that e power minus x, x power n minus 1. Okay. So there it is having integral 0 to infinity is nothing but simply we are representing as x greater than 0. That is from 0 to infinity. Okay. And alpha and beta are parameters here. Okay. So 0 elsewhere. Rest of the cases, the density function value is 0. Where the parameters also must be here it is greater than 0. So what are the parameters in binomial distribution we learned? N and P. And Poisson distribution, lambda. And next normal distribution, mu and sigma. And coming to gamma distribution, alpha and beta. So these are the parameters of different distributions. Of course, these two distributions coming under binomial as a discrete, and these distributions coming under continuous. Okay, in second unit we learned these two, and third unit we are learning these distributions. Okay, next, the special gamma distribution for which alpha is equal to 1 is called the exponential distribution. So if alpha is equal to 1, then we say that the gamma distribution is converts into exponential distribution. It means what we'll get here 1 by beta power alpha, we are saying alpha is 1. And next what we'll write gamma 1 x power alpha minus 1, that is nothing but 1 minus 1 e power minus x by beta. So this is the formula we write. If we substitute in place of alpha as 1 in gamma function. So here it is f of x is equal. So f of x is equal 1 by beta into gamma 1. But already we know that by using the gamma function properties, gamma 1 is equal nothing but what we are saying 1. So gamma 1 is 1, and if it is 1 minus 1 is 0, anything power 0 is 1. And what about remaining here it is e power minus x by beta. So it means simply we can define beta function f of x exponential distribution is defined as f of x is equal 1 by beta e power minus x by beta, x greater than 0. Okay, so this is the definition, we can say that. So it means if you know that gamma distribution, obviously we can get exponential distribution by taking the value alpha is equal 1. Okay, that is exponential distribution. And now see that what we discussed, same or not. Here, what about the parameter? Only one parameter, that is nothing but beta. So that's why we wrote here. If you see that binomial distribution also, we defined v of x n p. So x n p. So this is binomial distribution representation we write, or simply we write b of x. Okay. In the same way, here is y. It is representing whatever the parameters we are taking, just we are writing those parameters. Okay. And now already we said, so by taking alpha is equal to 1, we got it as 1 by beta e power minus x by beta, x greater than 0, and beta is also greater than 0. So same definition, see that the continuous random variable capital X has a exponential distribution with the parameter beta. Okay, so same akra there it is in place of exponential without gamma, and in place of beta there without alpha and beta, and its density function as usual. Okay, next, the mean and variance of gamma distribution is mu is equal to alpha beta and sigma square is equal alpha beta square. So this is mean and variance of gamma distribution, and if they are standard deviation is nothing but what we get, sigma is equal to square root of alpha into beta, and obviously exponential will get it if you know that gamma distribution simply by substituting in place of alpha as 1. So that's why here we got it as beta, and here it is beta square. Okay, so that one we are going to prove now. Okay, so our mean we said here alpha beta and variance we said alpha beta square. So we are going to prove here. So before that, first we need to know the properties of gamma probability density function. So there it is. What are the properties we said? The function what we are saying f of x, that is greater than or equal to 0 for all x. So that is one thing, and another thing is the interval minus infinity to plus infinity f of x dx is equal 1. So it means the total area under the curve is 1. So integral minus infinity to plus infinity f of x dx is equal 1. So these two properties we need to remember that. Okay, and what is the formula we are using for calculating mean? So for calculating mean in continuous random variable, what we are using, integral x into f of x dx from minus infinity to plus infinity, and variance is nothing but simply we write the formula e of x square minus e of x whole square. So e of x square minus e of x whole square. So this is the formula we are using for calculating variance. So this one is nothing but what we can write, integral minus infinity to infinity x square f of x dx. So this is we can write x square f of x dx minus e of x is nothing but what we can write, mu. So minus mu square. So by using this we can calculate variance. So and variance we are giving representation as sigma square or v of x or variance of x, and mean is nothing but simply we can write mu. So mu is equal to this one and variance is equal to sigma square. So these two we can calculate by using these formulas in continuous random variables. Okay, so that one only we are going to prove now. So first one, find the mean and variance of the gamma distribution. Okay, so we are going to calculate mean and variance of gamma distribution. Okay, so for continuous probability distribution, so what we are using the formula for calculating mean. So mean mu is equal to e of x is equal integral minus infinity to infinity x f of x dx. Okay, integral minus infinity to infinity x f of x dx. So this is the formula we are using for calculating mean. So for calculating mean, what we are using, integral minus infinity to infinity x into f of x dx. Okay, so here it is which distribution we are using? We are using gamma distribution, right? So this is we are using gamma distribution. It means we have to take the probability density function f of x is equal to what we have to choose, 1 by beta power alpha gamma alpha x power alpha minus 1 x power alpha minus 1 and e power minus x by beta. And the condition is very important, x greater than 0. So and rest of the cases we are taking the function is 0. So this is the function we are using. So for that, here we can substitute in place of this one simply, we can split as two subintervals. One is minus infinity to 0 x into f of x dx, one subinterval, and next plus integral 0 to infinity x into f of x dx. This is another subinterval. So total interval is minus infinity to plus infinity. But as for the function, we are splitting into two subintervals. One is minus infinity to 0, another one is 0 to infinity. As for the function, what we know that this is the function is valid only for the interval 0 to infinity. And rest of the cases, the function is what we are saying 0. So for that, so 0 into anything 0. So the entire this one is value is 0. Now we are going to calculate only this subinterval from 0 to infinity x into f of x dx. And f of x already we know that. This f of x we are taking 1 by beta power alpha gamma alpha x power alpha minus 1 e power minus x by beta dx. So that one we are going to calculate. Okay. So for that, simply here we wrote integral 0 to infinity x into f of x is here 1 by beta power alpha gamma alpha x power alpha minus 1 e power minus x by beta dx. Okay. So here it is with respect to what we are applying integration x. So obviously this is a constant. So for that simply we are writing this is out of integrand. So outside of the integrand we are writing. So for that here it is 1 by beta power alpha gamma alpha x as this x power alpha minus 1 e power minus x by beta dx. Okay. Now we are going to simplify this. So 1 by beta power alpha gamma alpha as this. So that one we are writing here. And next, here it is if we observe this one, integral 0 to infinity. So here it is if we observe this one, this is in the form of a power m, a power n. So here it is m is nothing but 1. So in place of this one, what we can write the formula a power m plus n. So that is nothing but x power 1 plus alpha minus 1. 1 plus alpha minus 1. Okay, and e power minus x by beta as this. E power minus x by beta as this we are writing. Okay, so that is the formula we are going to apply. After applying that, what you get here it is 1 by beta power alpha gamma alpha x power 1 plus alpha minus 1 e power minus x by beta dx. And now here it is if you see that, so simply we are writing, we are keeping these two in one bracket and minus 1. So there is no change in that as it is 1 plus alpha minus 1. Okay, e power minus x by beta dx. And for simplification here we are using gamma function. So this is in gamma function we did this problem. So integral 0 to infinity x power n minus 1 e power minus mx dx is equal gamma n by m power n. So this is the formula we are going to apply. So if you compare this one with this one, so 0 to infinity as this, x as this, in place of n what we have, in place of n here it is alpha plus